So it turns out that the executor service has a number of other interfaces that are related to it above and beyond the interface that defines the key methods that we will talk about shortly. And we're going to talk about those other interfaces because you have to have a vague idea of what they are before you can really understand the interface and how the methods work. So there are three primary interfaces that go along with executor service. One is runnable, which we've talked about before. One is callable that I mentioned briefly, but we'll talk about in more detail. And one is future, which we also mentioned very briefly, but we'll talk about in more detail. There are two interfaces used to define tasks, runnable and callable. Runnable, which we've seen before, so this is just a real quick recap, is a very, very simple functional interface that defines a one-way task, which means, as we've said before, it doesn't return a result. So that's pretty straightforward. Callable, which we haven't talked about in much detail, what we will focus on now, is also a functional interface that defines a two-way task that returns a result. And this is typically used to run two-way async tasks. The examples I like to talk about are, dropping a letter off in the mailbox. You don't just sit there neurotically waiting for something to show back up. First of all, if you drop a letter in the mailbox, it won't show up in the mailbox. It'll show up in your mailbox in your house or your apartment or your dorm. But secondly, it goes and runs asynchronously. Somebody else delivers it, and you get a response back if you get a response at some point. Callables are used to implement another pattern. Remember, we talked about runnables and how they're used to implement either the command pattern or the command processor pattern. Runnables can be used to implement the active object pattern, which is another pattern. This one is from the POSA 2 book, Pattern-Oriented Software Architecture, Volume 2 book that I wrote about 20 years ago. And this talks about a pattern that decouples the thread that invokes a method from the thread that executes the method. And one of the cool things about the active object pattern is you can actually get results back. You don't just do one-way calls. That's command processor and command are one-way calls, but active object gets results back from asynchronous operations. And at the heart of the active object pattern's ability to get results back from two-way calls is the concept of a future. And this is what's used to represent and control the life cycle of a task that has been submitted to run asynchronously. We can do several things with the future. We can retrieve the results of the task using several variants of the get method on the future. And we'll talk about what those do shortly, but you can get the results when they're done, or you can wait for them to be done. You can also use the future to be tested for completion. You can say, hey, future, is the asynchronous operation that you're running finished yet? Yes or no? You can say, is it done? And we can also test the future to see if it's been canceled. And if it's not been canceled and we want to cancel it, we can cancel it. So you can see that these are the methods. And these are methods that you'll have to use in the upcoming programming assignment. So we'll talk about how they work in more detail shortly. You can basically think of a future as a proxy that represents and controls the result of an asynchronous computation. That's basically what a future does underneath the hood. So what you can have is you can have some asynchronous computation running in some thread in a thread pool. And when that computation is done, then the result will be made available to the client, which can then, quote, get the result. I like to think of human analogies, human known use analogies for all these technical concepts, especially for concurrency, because it's really much easier in my mind to think about that as you learn the intricacies of the technology. So a good example of futures in everyday life are the concept of table tent numbers. So if you go to a restaurant, if you go to like Sun and Fork, I think it's called, which is over by 2525, and you place your order at the cash register, they don't just give you the food, they give you, basically, they give you like a big wooden marker, but it's a table tent number. If you go to certain fast food restaurants like a Wendy's and you order a food, they won't actually bring the food right to you. They'll give you either a table tent number or a slip of paper with a number on it. Right? That's the future. That's a token that can be redeemed to match your order with whatever you ordered when it's finished. There are other types of restaurants that have a different model, and we'll talk about the different models. So think about this from that point of view. The different models I like to talk about are the classic McDonald's model versus the classic Wendy's model. So the classic McDonald's model, they've actually changed this a little bit, but back in the day, McDonald's was all about inexpensive, super duper fast food. So you would go in, you would go up to the cash register, you'd say, I want a Happy Meal, or I want a Big Mac with fries and a drink, or whatever you wanted to order. You would give them the money, and then they would serve you synchronously at the cash register. How did that work? They would have pre-cooked a bunch of Big Macs or fish fillet sandwiches or whatnot, put them under a heat lamp. They would have a bunch of French fries in their containers, large or small, under a heat lamp, and they would actually often pre-pour Cokes or Diet Cokes or whatever and have them sitting right by the cash register. So when you placed your order, the cashier would turn around, grab the Big Mac out of the cash, grab the fries out of the cash, grab the drink out of the cash, turn around and hand you back your order, and you just stood there and they would hand you that back in real time. The problem with that, as you might imagine, is that putting the food in the cash meant it wasn't very fresh. So another fast food restaurant chain, Wendy's, came along, and their big thing was, we cook your meal to order. We don't give you food that's been sitting here in the heat lamp for an hour and a half getting all stale and moldy. We're going to do it for you on the fly. Well, how did they do that? They didn't want to have a situation where you'd have to stand there at the cash register waiting for 5 minutes while they cook your food to order. And why would they not want to do that? It'd be slow. And why would it be bad to be slow? Can't make the money, right? You're not going to be able to get throughput to bring in the return on investment people want on a per minute basis or whatever. So what they would do is you would go up, you would order, you'd say, I want a Wendy's burger and fries and a drink, and they would take your money, hand you a future, maybe give you an empty cup so you could go fill your own drink. That's about offloading work to the client, right? And then you would go off and you would, back in those days, you'd like read a paper, or you'd actually talk to your friends. What a concept. Nowadays, you'd text people or browse the web. But the point is that you would go off and they would cook the food, and when they were done, they would do one of two things. They would either bring the food to your table, because you'd put your little table tent number somewhere and they could find you, and that's what's called the callback model. Or you were obliged to, they would like call out your number, or you were obliged to walk up to the pickup window and say, hey, I've got order number 12, is my food done yet? That's what's called the polling model. And with a polling model, you have two choices. You can either walk up and say, is my food ready yet? And if they say, no, it's not, you say, okay, thanks. And you walk back to your table and keep texting your friends or whatever. That is what's called polling with no timeout, right? You just check, and if you're not getting served, you just go off and do something else. And then there's also a polling with timeout, where you go up and you say, hey, is my food ready yet? And they're like, oh, it'll be ready shortly. You're like, all right, well, I'm going to stand here for a minute or so because I want my food as quickly as possible. And if it still hasn't come in 2 minutes, I'll go back and text my friends or whatever. So those are two different models. There's a timeout-based model, and there's an immediate polling model. Both of those are polling models as opposed to callback models. And it turns out that what I just described is very much the way futures work, although they don't really have a callback model per se. We'll talk about that if you take my class next semester with a different framework called the CompletableFutures framework, which does have callbacks. At any rate, the way this all works under the hood is that you can submit asynchronous computations, tasks, via the submit method on the executor service. So you can say, I want to make a new executor service with a fixed size thread pool, just for sake of argument. And then I want to go ahead and submit a task. Here we might have a task that's going to multiply two big fractions and store the result. And then we can go ahead and submit that task. And what that does when we submit that task is that gives us back a future. So the task will then go off and run in the background in one of the threads. We have a future. And then at some point, we can get that future. When we get to a point where we're like, we really need that result. I'm really, really, really hungry now, so I'm just going to stand here and wait to get my result. I get my food. I can call the get method, and that will block the thread until the result is available. But you typically don't do that right away, because if you did that right away, it would defeat the whole purpose of doing asynchronous computations. You want to let the computation run in the background, and you go off and do something else for a while, and then get the result later. And you can either do this by blocking, which is this approach, or you can call a timed version with either a timeout of 0 or some timeout that's greater than 0. One of the consequences of futures, let's see if I can rerun this and you can watch it, is that the order in which things are returned may be different from the order in which they're invoked. So if you go to a fast food restaurant and you order some really complicated meal, but the person right before you ordered something very simple, their result may come out before you, their food may be done before yours, their order may be done before yours, even though they went first. Sorry, let me rephrase that. You go first, you order something complicated, someone else comes along and orders something simple, even though you went first, they'll get their order before yours. So that's an example of out-of-order processing. And if you're going to be using asynchronous computations, you have to be prepared for out-of-order results. That's just part of the game. And if ordering is important to you, you should either not use asynchronous operations, or you should find some other way to order things as the results finish, like give some kind of an ID, an order ID, so you can rearrange the results later if you need to. Futures are applied in the active object pattern, as we talked about before, so you can do the asynchronous computation in some thread in the thread pool, and then the client can get the results. Of course, the client was what invoked the operation in the first place, but it didn't block, it got a future, and then it does its thing in the background. There are other future mechanisms that are provided in the executor service. So there's other subclasses of future, or subinterfaces of future, extensions of future, that are used to actually implement the executor service. So one thing is called a future task. We'll talk about that later. And that's basically used to perform some computation in the background and then store the result someplace that can be picked up when the computation is finished. We'll talk more about that when we talk about some of the other mechanisms that are available to actually implement the future interface. There's also something called a runnable future, which essentially has a run method that does the processing and then allows the future to give access to the results. So this gets both methods. So there's runnable future, which is a future, and then there's future task that inherits runnable future and adds some more stuff. There's also another framework called CompletableFuture, which is really cool, which is a much more powerful implementation of future that allows dependent actions to be triggered upon the completion of asynchronous operations. Those of you who took the class last semester remember that, because we did a whole unit on that. We won't talk about that here, primarily because it's actually not part of the Java Executor framework. The Java Executor framework came in Java 5, which was 2004 timeframe, and CompletableFuture came in Java 8, which was the 2014 timeframe, so about a decade later. And so as a result, it's just not integrated at all, which is kind of a shame, but that's the consequence of backwards compatibility. So we'll cover that in another context. The executor service also forms the basis for a bunch of other cool things in the Java Executor framework. So in particular, there's something that's called the thread pool executor, which is used to implement a lot of those predefined thread pools like fixed thread pool and cache thread pool. There's something called the fork join pool, which is used to implement the work stealing pools. There's a scheduled thread pool executor. And all of these things indirectly implement the executor service interface, although they do it by extending something called the abstract executor service class. And we'll take a look at that later. There's a lot of common methods in this class that are inherited by thread pool executor, fork join pool, and scheduled thread pool executor. The main point here is just that there's interesting ways of being able to take the base interfaces and then extend them and implement them to provide different kinds of thread pools within a common API. That's the key point to come away with from this.